Hello, my name is Timothy Trippel, and I'm a PhD candidate at the University of Michigan. Today, I'm going to tell you about a framework we developed to estimate the susceptibility of your integrated circuit layouts to Foundry side attacks. This is joint work with Kang, Shin, Kevin Bush, and Matthew Hicks. Integrated circuit hardware is the foundation of all computing systems. The foundational piece of hardware in the computer I'm using to prepare this presentation is a microprocessor, and above this microprocessor sits several layers of software. Even if each software layer has been formally verified to be 100% bug-free, any flaws in the hardware can completely undermine any of the software layers above. The software community has done a great job developing mechanisms to both identify and prevent vulnerabilities in attacks. These include things like trusted execution, symbolic execution, fuzzing, ASLR and DEP, and secure boot. As such, this has forced attackers to lower levels of the system, i.e. attacking the hardware, since attackers simply don't give up. Making matters worse, economic forces have made developing secure hardware challenging. Developing a digital integrated circuit requires several steps, each heavily augmented with computer-aided design or CAD tools. Of all of these steps, the fabrication step is by far the most prohibitively expensive. To build a leading-edge fab today is expected to cost almost $20 billion. As a result, most semiconductor companies and even nation states are fabless, meaning they outsource fabrication often to one of two companies, Samsung or TSMC. Outsourcing, combined with the nanometer scale black box nature of fabricated ICs, presents a security risk. How do we know our circuit layouts encoded in the GDS2 format are not being modified at the foundry to include a backdoor or a hardware Trojan? A hardware Trojan is an intentional hardware flaw designed to alter the functionality of the victim circuit. Similar to unintentional flaws or bugs, hardware Trojans create a hardware foothold for attackers to subvert higher levels of software. While researchers have developed effective defenses against recent hardware bugs, the same response has not been taken against hardware Trojans. Unfortunately, the defenses we do have against hardware Trojans remain largely unused. Why is this? Well, as we will show, existing defenses are either impractical or ineffective, and thus not worth the deployment overheads that accompany their use. To date, researchers have developed two main classes of defenses against Foundry-side attacks. The first, prevention techniques, and the second, detection mechanisms. Unfortunately, in both cases, researchers have shown numerous ways to bypass all of these defenses. As it turns out, preventing or detecting hardware Trojans is extremely challenging, as researchers have demonstrated stealthy Trojans that can be constructed with only two additional gates. So which approaches should we focus on, and how can we improve them? I think we can all agree prevention is preferable to detection if prevention is possible. And of the prevention techniques developed so far, layout filling is the only approach that follows Kirchhoff's second principle of avoiding security through obscurity. In this work, we aim to address two key questions to provide some clarity with respect to the real threat posed by hardware Trojans. The first, should we even care about hardware Trojans? How challenging is it to insert a Trojan at fabrication time? The second, why are current preventative defenses ineffective, and how should we improve them? To answer these questions, we need insight. We need to understand what makes a circuit layout amenable to attack and why preventative defenses are inadequate. To address these questions, we develop an open source IC layout analysis framework called ICAS, or Integrated Circuit Attack Surface, that estimates the susceptibility of integrated circuit layouts to fabrication time Trojan insertion. To understand how ICAS works, we need to understand one, how IC layouts are constructed, and two, how one goes about inserting a Trojan into a layout. As many of you probably know, integrated circuits are fabricated on silicon wafers, where each wafer contains several copies of the same circuit die. Each circuit die is a three-dimensional structure where the bottom layer, known as the device layer, contains all of the logic gates or physical transistors that are organized on a grid known as the placement grid. Surrounding the placement grid are I/O pads that enable the chip to communicate with the outside world. Stacked above the device layer are several metal layers where wires are routed to connect the transistors on the device layer below. As you can see in the side view of the metal layers, wire sizes increase as you go higher in the stack. As we will use ICAS to show, the fundamental reason circuits are vulnerable to hardware Trojans is because the density of the device layer is less than 100%. And this is for two reasons. The first is that the wires used to connect the transistors are often larger than the transistors themselves. And the second is that the CAD tools that automate the place and route process employ heuristics to identify viable routing solutions for a given layout. Reducing density makes it easier to find these routing solutions. An attacker looking to insert a hardware Trojan into a victim circuit layout has a choice of three different Trojan types to implement. The first is additive, the second is substitution, and the third is subtractive. In this work, we focus on the threat of additive Trojans, or Trojans that require adding additional components and/or wiring to the layout, as these are the stealthiest and most controllable, since an attacker can create complex triggering mechanisms and is not limited to using only existing components and wiring already available in the layout. As such, they are also the most widely demonstrated in the literature. There are three steps a Foundry side attacker must take in order to insert an additive hardware Trojan into a circuit layout. The first is Trojan placement. During Trojan placement, an attacker must locate empty placement sites on the device layer to accommodate their Trojan components. The second is Trojan victim integration. This is where an attacker must locate an unblocked segment of a security critical wire to connect their Trojan wire to. The third is inter-Trojan routing. In this step, an attacker must route their Trojan trigger/payload components to the integration point. These three steps form the foundation for the three metrics implemented in the ICAS framework of trigger space, net blockage, and route distance. The ICAS framework takes as input a GDS2 file encoding the circuit layout and the final optimized netlist from the place and route stage, and computes a set of security metrics that detail the placement and routing resources available for an attacker to insert their Trojan. The ICAS framework consists of two main components, NEMO and GDS2 score. In the interest of time, we'll be focusing on the GDS2 score stage, as this is the main component of the ICAS framework that computes the security metrics mentioned in the previous slide. So what does each metric measure, and how does this translate to attack difficulty? The trigger space metric characterizes the size and frequency of contiguous unused placement sites on the device layer. In doing so, it characterizes the difficulty of carrying out the Trojan placement step or locating empty placement sites to add Trojan components. To reduce insertion time and complexity, it is likely an attacker will pre-design a Trojan ready to be dropped into a GDS2 layout as soon as it comes through the Foundry door. If their Trojan has a large footprint, they will need to locate a large contiguous block of unused placement sites to accommodate their Trojan components, or be forced to scatter their Trojan components across the chip, making routing much more challenging. The net blockage metric characterizes the percentage of surface area of designer annotated security critical nets that are blocked by nearby components and/or wiring. When an attacker integrates their Trojan into a victim design, they must locate a surface of an unblocked security critical net to attach their Trojan logic to. The fewer locations available, the more challenging this step becomes. Lastly, the route distance metric combines the results from the trigger space and net blockage metrics and computes the minimal routing distance between contiguous unused placement sites and unblocked surfaces on security critical nets. In doing so, the route distance metric expresses the difficulty of the intra-Trojan routing step. Longer route distances between placement site and security critical wire pairs makes implementing timing critical Trojans more challenging, as longer route distances correspond to higher capacitive loading and thus longer signal transition times. What's unique about the route distance metric is that when a designer overlays a set of resource requirements for attacks they care about, the route distance metric illustrates the overall attack surface for a given circuit layout, a unique feature we illustrate in our evaluation. We choose to implement the three metrics of trigger space, net blockage, and route distance as they encapsulate a majority of additive Trojans demonstrated in the literature, including those that only add transistors or only wires, and those that add both. Additionally, ICAS metrics are flexible and can be interpreted individually or comprehensively depending on the Trojans a designer cares about. While we hope our metrics serve as a comprehensive starting point for quantifying IC layout security, we recognize that these metrics are far from complete, which is why we designed ICAS to be extensible, enabling users to develop their own metrics as they expand the set of Trojans they care about. To evaluate ICAS, we use it to uncover the effectiveness of existing layout level defenses, for which there are two types, undirected and directed. In doing so, we demonstrate the power of ICAS insights in showing where IC layouts are most vulnerable to specific attacks. We study over 60 layouts of 3 open source circuit designs, including an OR1200 processor, an AES accelerator, and a DSP accelerator. Each design was laid out on an IBM 45 nanometer process using Cadence tools. If you recall, the net blockage and route distance metrics are targeted metrics that measure characteristics about designer annotated security critical nets. While designers might classify different nets as security critical depending on the deployment scenarios they are considering for a specific design, we select a set of nets across each design that we deem security critical based on demonstrated attacks from the literature. For the OR1200, we select the supervisor mode bit nets. For the AES, we select all 128 key bit nets. And for the DSP, we select the next out interrupt signal nets. The two types of layout level defenses against fabrication time additive Trojans are one, undirected, which tune layout parameters to probabilistically constrict placement and routing resource utilization, and two, directed, which constrict resource utilization around security critical wires. Using ICAS, we'd study the effectiveness of each defense at thwarting 4 different additive hardware Trojans demonstrated in the literature, including the A2 analog and digital attacks, a privilege escalation attack, and a key leak attack. For each attack, we list the number of additional gates each attack requires and the corresponding number of placement sites occupied by these gates on the 45 nanometer process we studied. Additionally, for each attack, we indicate if it is timing critical, meaning an attacker is constrained from utilizing long route distances that would make their attack non-functional. First, we compare the attack surfaces of 6 different OR1200 circuit layouts that demonstrate the effectiveness of undirected layout level defenses that either 1, constrict placement resources by increasing the core density to various degrees, or 2, constrict routing resources by tuning performance constraints like maximum transition time. We plot route distance heat maps detailing the attack surface across each IC layout. Each column within each heat map is a histogram of the distances between unused placement sites of a given size, indicated on the x-axis, and unblocked security critical nets. Distances, indicated on the y-axis, are reported in standard deviations from the mean net length observed in a given layout, since wire lengths are always relative to a layout. Overlaid on each heat map are color-coded rectangles that indicate the layout resources an attacker can utilize to construct a specific Trojan, and a number indicating the number of possible ways the Trojan could be constructed. These results confirm the intuitions behind layout level defenses that constricting either core density or maximum transition time constraints during the place and route process produces layouts that are more compact and thus more secure. However, unfortunately, these results also show that there are thousands of ways a Foundry side attacker can insert hardware Trojans even within the densest circuit designs. Next, we compare the attack surfaces across 2 different layouts, each of the OR1200, AES, and DSP circuits, with and without a directed layout defense deployed. Unlike the undirected defense, this defense constricts placement resources locally rather than across the whole chip by filling unused placement sites near security critical wires with functional logic gates. To evaluate this defense, we simulate the best case deployment scenario, whereby we fill unused placement sites near security critical wires first until we achieve an overall chip density of 95%. We utilize the ICAS route distance metric again to illustrate the attack surfaces of each circuit layout with respect to 4 Trojan designs from the literature. You may notice that not all Trojans are overlaid on each heat map. This is because some Trojans are design specific, such as the key leak Trojan, which targets a crypto core. ICAS metrics reveal that directed layout filling does increase the security of IC layouts by pushing unused placement sites as far as possible from unblocked security critical nets. But for small Trojans like A2, thousands of attack configurations still exist. Circling back to the 2 questions we posed earlier, one, should we care about hardware Trojans? ICAS results say we should, since modern IC layouts have a plethora of layout resources for Foundry side attackers to exploit, even with state-of-the-art defenses deployed. 2, why are current preventative defenses ineffective? If you noticed, layout level defenses are primarily placement focused. They decrease the amount of unused placement sites for attackers to exploit. However, since it is impossible to achieve a core density of 100%, this is futile. So where do we go from here? What about a routing-centric defense that guards potential victim integration points or unblocks security critical wires? With ICAS Insights, we aim to enable IC layout engineers to design new mechanisms to harden their circuits against the modern-day threat of the untrusted Foundry. Thank you for listening to my talk, and if you have any questions, don't hesitate to reach me via email or during the live question and answer session.